So now we're going to look at some real-life photoelectron spectroscopy graphs, and in order to help us, we're going to refer back to electron configurations. And my cat has again decided to jump in and say hi. Say hi, and now go away. Yeah, did not like that very much. So the best graph to start with is one that deals with hydrogen. I want to point out to you down here this change in UE really means ionization energy or binding energy, and the number of electrons is written on the y-axis. They've even been so kind as to write the numbers here, which is not very likely to happen normally. But let me jot down for you what the actual electron configuration of hydrogen is. It's 1s1, or if you're like orbital notation buff, that would be 1s with an electron. And if you take a look here, what this right here is showing you is that it takes 1 point, and this, by the way, is the amount of energy that is required to cause this electron to be removed. It requires 1.31 megajoules per mole. And if you look at the height, we're pulling off 1 electron. So in hydrogen, there's only 1 electron in the hydrogen atom, and if we were to draw it in a very poor way, we'd have 1 electron in the 1s. And after we knock that electron off, the amount of energy that's inputted into here, that is this right here, and it's 1.31. Now, if we take a look at helium, helium looks very similar, except it's 1s2, and if we were to take a look at the orbital notation, it'd be 1s with 2 electrons. Now take a note here at a couple things. One, do you notice how here the amount of energy that's required to pull these electrons off is 2.37, whereas here it was 1.31? And that should kind of make sense, because if you think about it, the helium atom, it has 2 protons and it has 2 electrons, whereas the hydrogen atom had 1 proton and 1 electron. So each of these electrons is going to feel a greater pull, and that means that it's going to be harder to pull them off, which is why each of these 2 requires 2.37 megajoules per mole. Now, if you notice here, the height number of electrons, if you took a look, again, it'd be 2. Don't get too comfortable with them actually having numbers down the side, because a lot of the graphs don't have that. But it's pretty easy to see how the difference between a 1s, 1s1 and a 1s2 is that the height represents 2 electrons versus 1, and the energy that's required to pull them off is a little bit greater. Let's move on. What if we went to lithium? If we look at lithium, lithium is 1s2, 2s1. Agree? So if we take a look at this, well, what do these bumps represent? Well, do you see how we have 2 electrons right here at 6.26, and we have 1 electron here at 0.52, and if you're wondering how we get the electrons, it's right over here, right? And if you notice here that the 6.26 is the amount of energy that's required to remove these 2 electrons from the atom, and 0.52 is the amount of energy required to remove this 1 electron from the atom. And that corresponds rather nicely to this. The 2 electrons that are in the 1s would be right here. And the 1 electron that's in the 2s would be right here. And so you can kind of see that and if you compare it back to the previous slide, you see how it was 1.31 and 2.37, but as you start adding more and more protons to the nucleus, each of the outermost electrons is going to feel a greater pull, a greater effective nuclear charge, and that's why it's going to be pulled in a little more tightly. Similarly, if we go one more to beryllium, and if we were to draw beryllium's electron configuration, it's 1s2, 2s2. Now here's what's kind of cool here. You can notice here that, see how the height of both of these peaks is exactly the same? Again, we have the numbers here. It's very rare that that happens. So normally what you're going to have to do is you have to look at just where these peaks are and see if they're similar to each other, and you can kind of do like your own little gradation here. But here they have done it for you. Again, it should make sense that it's going to require more energy to pull the electrons off of the 1s, and here we have 2 electrons in here, and a little bit less energy to pull off electrons from the 2s. Also notice that if you compare this number to this number, see how this is 11.5 and this is 6.26? Again, it makes sense, hopefully, because here you have 4 protons for every 1 electron that is pulling in, so the effective nuclear charge is greater, which means it's going to require more energy to pull these off. So essentially, the trends that we were following before about size kind of impacts us here, and all the rules for ionization energy impact us as well. So the greater the effective nuclear charge, the stronger the pull on every electron. Let's keep on going here. What if we deal with boron? And if you look at boron, again, I'm just moving across the periodic table. It's 1s2, 2s2, 2p1. Now, if you take a look here, and this kind of makes sense, hopefully, do you see how I have 2 electrons here, 2 electrons here, and 1 electron here? So 2 here, and 1 here. Wouldn't this correspond to the 1s2 because it's the hardest to pull off those electrons? This would be the 2 electrons in the second energy level, and this would be the electron in the p orbital. Now, again, take a look at the height, the relative heights of these 2 peaks. They're the same because the y-axis, how high up you are, represents the number of electrons. So 2 and 2. The number right here, 19.3, is vastly higher than the 1.36 because, again, these electrons are being held more tightly to the nucleus because there's more protons and they're in an inner shell. This is in the second energy level, which is the outer shell, and it's not going to be held as tightly. And then these guys are going to be held even less tightly because the probability of finding an electron in the 2p is going to be a little bit less. Now, carbon, again, I'm going to kind of go through these 1s2, 2s2, 2p2, and if you notice here, the same kind of pattern emerges here. Now, since the height of all 3 of these is identical down below here, so if we take a look, right, my pen's a little bit off center here, this one, and this one, they all have 2 electrons. This would correspond to the electrons that are closest to the nucleus, which would represent 1s2. These would be a little bit farther out, which would be 2s2, and this would be our 2p2. Kind of getting the hang of this? Let's try another one. Let's jump to this one right here, neon. And if I were to draw the electron configuration, it'd be 1s2, 2s2, 2p6. And again, if you notice here, we can count the lines here, but this clearly is 6, and these both right here are 2 and 2. So this right here is going to correspond to 1s2, 2s2, and 2p6. Notice the number here. Notice how it goes up so much higher than the previous, 84 megajoules per mole, and then 4.68. That's because as you add more and more protons to the nucleus, as you keep on adding them in, the greater effective nuclear charge is going to pull all these electrons in that much more tightly. Again, the other thing I want to remind you of is that it's very often we are not going to have these numbers right here. All you're going to have is you're going to have these 3 heights. And so if you took a look at this and you're like, well, how do I know how many electrons there are? If you take a look at this, at the height of this right here, and you kind of rolled it right into here, if you were to take this height, couldn't you put that in essentially 3 times into this? So if we know that these 2 are 2, then this one here must be 6. Now let's look at sodium. Sodium is 1s2, 2s2, 2p6, 3s1. And if you take a look at the numbers and how the peaks and how they match up, it kind of looks the same way again. So take a look over here. We have the 1s2, the 2s2, the 2p6, and the 3s1. Notice again, these heights right here are identical. This height here is half the height of this because it's only 1 electron, and this is 3 times the height of these. I'm only reminding you because this is a courtesy. They're giving you these numbers on the side, and it's very unlikely that'll happen. Also be aware that the number that we have here for the number of the ionization energy, look how it keeps on getting bigger and bigger comparatively. You have 104 here versus 84. Let's try another one. This is even a little more crazy. Let's take a look at this, and if you take a look at the heights here, and let's say we didn't even know what this was, couldn't we look at the board and go, all right, there's 2 here, there's 2 here, there's 6 here, there's 2 here, and there's 6 here. Wouldn't that fit rather nicely to a 1s2, 2s2, 2p6, 3s2, 3p6? Again, look at the amount of energy that's required to pull off this one, 309. Even to the ones on the previous page, 104 to 309. So it should be reminding you that the power of the adding of protons is really, really potent in holding electrons to an atom. And that means that when we're adding more electrons into the center, the electrons that are closest to not electrons, we're adding more protons to a nucleus. The electrons that are in the first energy level are going to be held so much more tightly. Let's try one more. And this one here is a big one. because it looks really, really confusing. So let's just take a look at this and see whether we can make sense of it. Now, if I were to, I'm going to start off by writing what the actual notation is for this. 1s2, 2s2, 2p6, 3s2, 3p6, and then what? 4s2, 3d1. Yeah? This would be the configuration if we drew it all the way out. So let's walk through and see what we have here. Notice again, there's 2 electrons right here, which would correspond to the 1s2, right? And it has a huge amount of energy required to pull them off. Then this right here, this is the same height with 2 electrons that are being pulled off. Here you have another 2 electrons, and that would correspond to the 2s2. And then here you have triple the height, which would be our 2p6. And then again, we're down to 3s2, 3p6, and here's where it gets a little bit tricky and or I find really interesting. Do you notice here that we would, in terms of the amount of energy, the 4s has less energy than the 3d. However, in terms of where they're located, and again I'm going to draw a very static version of this. So let's say this is the nucleus, and you have the first energy level, second energy level, third energy level, and fourth energy level, right? The fourth energy level, the 4s, is farther from the nucleus than the 3d. So when I'm pulling electrons off of an atom, it's easier for me to pull electrons off of the 4s than it is for me to pull electrons off of the 3d. Because the 3d is going to be more tightly held by the nucleus. So when we're looking at these 2 peaks right here, it's really important to realize that even though the amount of energy that the 4s has is less than the amount of energy that the 3d has, how tightly the 4s is held is less tightly than the 3d. So this is actually our 3d1 right here, and this is our 4s2. So because this is the fourth energy level, and because this is the third energy level electrons are going to be held more tightly, so 0.77, than the fourth energy levels, 0.63. Even though the orbital itself, the 4s, has less energy. It's all about distance. So the farther away, the least tightly you're held. Less tightly held. Now, I will say this. It is incredibly likely that if you see a photoelectron spectroscopy graph, that'll look like this guy right here. Why? Because they want you to get tripped up on this part right here. Hopefully this has helped you. We can try some more of these in class. Thanks. Bye.